Imagine a small space delta x whose probability density is px. Stretching or shrinking the space does not change its probability. Thus, if a function f scales the space to give delta z has the same probability as delta x. This gives us a simple relationship. Absolute value of delta z times pz is equal to the absolute value of delta x times px. Now you can approximate any function by dividing it into tiny rectangles. It is not hard to see that the smaller the width, the better the approximation. In the limiting case, as the width approaches 0, we get this relationship, which can be written as if we have more than one samples, the relationship becomes. Now, let's take a closer look at this equation and try to understand it geometrically. If you transform a value x0 into z0 using a function f, the slope of the function f at x0 multiplied by the PDF of z0 is equal to the PDF of x0. This equation is the key idea behind normalizing flows. But how exactly can we use this relationship to examine the probability distribution of x? The idea is simple. We want to maximize the log likelihood of x, which is the sum of these two quantities. We know what this term dz by dx is, but we don't know what the PDF of z is. So what you can do is, you can decide the PDF of z that you would like to have. Then you can try to find the right function f, which gives you the desired distribution. Thus, maximizing this sum will maximize the log likelihood of x and also learn to map x into a uniform distribution z. Here we assume that we would like z to have a uniform distribution. Here is a better look at how x gets transformed into z before and after training. For a transformation from x to z with the given relationship, the function needs to be invertible. This is because we don't want 2 points x1 and x2 mapped to the same location z, and also we would like to be able to calculate x for a given z. Thus, we need a function for which f inverse exists. In 1D case, such a function looks like continuously increasing or decreasing. A special class of such functions is cumulative distribution functions, or CDFs. A CDF is basically area under curve of a PDF. It has these two properties. Now, let's see how we can create bijective functions using CDFs. If we take a weighted combination of CDFs, we get a function which is also continuously increasing. This means it still satisfies our requirement to be invertible. If the sum of these weights is equal to 1, we get a nice property. The sum of these CDFs is a CDF itself. This can be seen easily using these two equations. This is a visual of the entire process. A function f is a linear combination of CDFs. We want to learn the means and standard deviations of these CDFs and also the weights used to combine the CDFs to get the function that maximizes px while also making pz as close to uniform as possible. Note that this function maps to values between 0 and 1. Now, we fix the PDF of z to be uniform and maximize the sum of log pz and log dz by dx. This gives us a function f which maximizes px while also making pz as close to uniform as possible. Let's break down this expression dz by dx into smaller components. Remember that the derivative of a CDF of a variable x with respect to x is the PDF of x. This gives us the following expression for dz by dx. Thus, we now have an expression we want to maximize. We know both the components of this expression. Maximizing this expression is the same as minimizing the negative of this expression. Let's take a look at how this is implemented in PyTorch. We can divide the implementation in three parts: data, model, and loss calculation. We usually already have the data x with an unknown distribution, but for this tutorial, let's create x using a mixture of two Gaussians. We create a dataset using the standard PyTorch API and create a training set with 2000 samples and testing set with 1000 samples. We decide to have a batch size of 128. This is pretty much all we need for the data part. Let's take a detailed look at how the model is implemented. Our model here is a sum of different CDFs. Let's fix the number of CDFs and call it n_components. We also want to learn the weights which are used to combine these CDFs. Since these weights are all positive and sum to 1, we can take n components numbers and pass them through a softmax function, the output of which will give us the weights which are all positive and sum to 1. Now let's define all the parameters which we want to learn. We define the mu's and sigmas of each of the n component distributions, but instead of sigmas, we use log sigmas for numerical stability. Then we define the logits to get the weights. Logits are the inputs to the softmax function that will give us the weights to combine these CDFs. Let's take a look at how these different parameters interact with the input to give us the output. The model simply implements these steps which we saw earlier. The model gives us two things, z and dz by dx. One minor but important point is to be familiar with the dimensions of your input, intermediate, and output tensors. This helps not only in debugging, but also making better use of features like broadcasting. And that takes care of the model part. Our loss function is simply the negative log likelihood of our data, which is just the sum of the outputs of the model. Then we can write some boilerplate code to train and evaluate the model. I won't go much into this since this is pretty standard. Let's take a look at the learned function f and the predicted distribution of x. As you can see, the predicted distribution matches closely with the actual distribution of the data. This was possibly the simplest case to show the idea behind normalizing flows and how to implement them. In the next video, we will look at how we can use more than one normalizing flows in sequence to get more powerful models. The link to the code is available in the description below. Thank you for watching.